Before we wrap up for this week, I want to go into some examples of state and go into some details about state that may highlight some caveats and gotchas that we'll run into as we start using this concept of a system to solve robotic problems. So if you'll recall, our state x was a mathematical quantity that we invented that encoded the time history of inputs to our system. All of our inputs u for time tau less than t is captured in state x of t. This may perhaps be contaminated by some noise. In this case, I'm talking specifically about the W noise, the part of the noise that is stateful. But more specifically, it's that mathematical quantity that allows for the output to be written as a function of the state and any current information. That is, it obeys the Markov property. Or in other words, there exists some function h such that the output at a particular time instance t, at any time instance t, can be expressed as that functional relationship h of just the quantities x of t, u of t, optionally depending on how we define x, v of t for some unknown quantity v, and possibly t. So we need to come up with a state, or we would like to come up with a state, that enables us to write this statement. And it's important to note that this statement, for being able to write this statement, being able to obey the Markov property, depends on what that output actually is. So as an example, in our robotics problems, we considered conflating the idea of a task objective with some output. So let's consider the example of a robot that's my arm. So we have my arm, perhaps my hand is at the end of my arm, and the task that we would like this robot to do involves the environment, which is the board. And we'd like to draw on the board. So the way we enable this, the way we enable our system, we're going to have some inputs to our robot. And the inputs are going to be motion commands to my hand. I can move it in or out, I can move it towards the board or away from the board, I can have a bunch of motions. And so perhaps I can command it to go out, towards the board, down, and then away from the board. Come in a bit, towards the board, down, away from the board. And so we have this set of inputs, this time history of inputs, which is the motion. And we want to be able to collect that entire time history of inputs in such a way that when we describe the next output, whatever that output may be, all we need to know is a single quantity, whatever that quantity is. So perhaps the task objective would be to get the hand to a specific point on the board. And in that case, the output would be the path or the position that this marker, the tip of the marker, will take to get to where it needs to be. The output of the robot system will be where my hand is so that it can push the marker relative to the board. And so one quantity that we can compute, that we can encode, that captures the time history of inputs is simply the current position of my hand. And when my hand is here, all I need to do is say, move out and then towards the board to get me there. And it doesn't matter whether I was in this position from my hand in my pocket or from my hand giving a high five. All that matters is that my hand is right here, right now. However, so in that case, we can say that the state is going to be just the position of my hand, the position of my marker, and that captures the entire time history of motional impulse. However, if my task were not just to get the marker to a particular point on the board, but rather to draw a particular image on the board, well, now it does matter whether my hand had been coming from playing a piano or from actually drawing two lines on the board before. And in this case, simply the position of the robot, the position of my hand and the marker in my hand, may not be a state for a different set of outputs. When the output was just where my marker is, then the state was allowed to be just the position of my hand. When the output involved the entire drawing, we're going to need to come up with a new representation, a new quantity that captures what has already been drawn, so that we can determine, we can plan for drawing the rest of the image. So that's one important thing to note, is that the choice of state will depend on the problem to be solved. And if there's just one problem, you can go ahead and create a state and go through the math and come up with solutions that work well. Perhaps in the course of your engineering process as a roboticist, you may have a problem to be solved now and anticipate some additional problems later on. It may be worth coming up with a state representation that accommodates a much broader set of system outputs or correspondingly tasks that can be addressed by that state. In practice, the world, the entire physical world, the real world, is a complex, highly involved, highly intricate system that there may be many challenges, many tasks, that every choice of state will inherently limit the set of tasks and objectives that can be described using that particular mathematical formulation. Now, I'll get into the details, I'll get into this concept of state representation a little bit more towards the end of that. But to get a clearer picture or to sort of explain a little bit more detail about this, let's go ahead and give a little bit more precise example of this notion of state as it relates to the time history of inputs. So in particular, and especially within this concept of relating to robots and robotics, let's consider motional inputs. If we're engaging with the physical world, if we're engaging with the real world, we're going to need to move through space, through the thing that we call reality. And so most robotic systems will involve some kind of inputs to that robotic system that involve motion through space. And so, as we saw here, there is a quantity that we can derive from a time history of motion inputs, which is the positional state. And if we, for a large number of objectives, for instance, just getting my marker to the start of the smiley face, that quantity will be a state of the system. So let's come up with ways of describing this state as a mathematical quantity, as a specific mathematical object. So, for the sake of simplicity for now, let's consider a planar environment. So, not the entirety of reality, not all of space, just the whiteboard right here. And so we don't have any ability to move our our pen in or out of, towards or away from the whiteboard. It's always just at the whiteboard. And all we care about currently, the set of outputs that of the robotic system, which is my arm, that we care about, is just where that tip of the marker is. In this case, we can then define our state as just the position of the tip of the marker. And how might we describe that as a precise mathematical quantity? Well, we can come up with a number of different things. Let's say from here, we'll describe this position as a numerical quantity capturing the length away from the length of this path away from the rightmost edge of the whiteboard, and the height of this point away from the bottom edge of the whiteboard. And so we can define our state, our positional state, that captures the entire time history of motional inputs to my hand in terms of these two numbers. We're talking now about a continuous state, because this L can vary arbitrarily, similarly this H. So we're talking about a continuous space system. We've described the state in terms of a particular set of two numbers, the distance from here and the distance from here. We didn't necessarily need to do that. We could instead have defined another state representing the same series of inputs, the same series of motional inputs that resulted in the tip of the marker being right here. We could have instead chosen to represent this time history of inputs by the distance away from the bottom right corner, right, left, I don't know, bottom corner of the whiteboard, and then perhaps the angle of this connecting line from the horizontal edge of the whiteboard. Again, these are both continuous these are both continuous variables. Can take on any value. Can take on any value. In both of these cases, we have that x is an element of R2. So what does that give us? What does this tell us? At least in this representation, with these two points, the state is of dimensionality 2. The size of the state space is 2. We are in a two-dimensional state space. The same history of inputs can be encoded in multiple ways. In this case, they've been encoded in two different ways, two different mathematical quantities that are both the same dimensionality. This brings up a question. Is this actually the dimensionality can we come up with a representation of a different dimensionality? Will this always be a two-dimensional representation? Hold on to that thought, because we'll come up with, when we start looking at a little bit more complicated of an example, we'll come up with different ways of representing states, representing the same state, where they aren't the same dimensionality. Now, I will assert for now that there is no representation of this state that has dimensionality 1. That is an element of R1. Now, some of you maybe play around with recreational mathematics and will want to bring up the fact that R1 and R2 have a bijection. But we're operating in the real world, where everything needs to be smooth, and there's no smooth bijection between R1 and R2. And so this space is of dimensionality 2. Now, what if we consider a different example? This was a planar environment, and we were only considering the marker tip. Let's stay in this planar environment, but instead consider our eraser. Now we have an eraser right here. And what I'd like to do is erase that one eye. Now, if I were to take this eraser and put it in this position, however I get there, I can take some time history of motions and put it up in this position, and then wiggle it up and down. That eye doesn't get erased. However, if I were in that same position, the same distance away from the edge and the same height up from the bottom, or perhaps the same distance away from the bottom corner and at the same angle, but instead of being here like this, I was instead holding the eraser in this orientation. Now when I move it up and down, the system does get, the eye does get erased. This eraser has some extent. It's not just a single point like the tip, but it has some collection of points that define this object. A general term for this is a rigid body. And what we can say is that when we have this rigid body, not only do we have inputs for moving it left, right, up, and down, we also have inputs that can change the orientation of the rigid body relative to the environment. So now we have more inputs that are available to us rather than when we were just considering the motion, the tip of the marker. Which means now if we're trying to encode more information, we're probably going to need to have a state that contains more information. And so perhaps we can throw on an additional thing that says, let's consider not only the distance away from the edge and the height from the bottom edge, but also the angle that this eraser makes with respect to the bottom. And now we can have some new state that has still the same position. We'll pick a point, maybe the center of this, and now compute the distance from the edge and the height from the bottom. And we'll also throw in an orientation. We'll call it alpha. We're still in a planar environment, but now we have a state space that's an element of R3. There are 3 real value numbers that our system can be in. Again, the system here being now this eraser. So the size of this state space is 3. This is a 3-dimensional state space. But speaking of that, when we hear the term 3-dimensional, the word dimensions has taken on additional characteristics when talking about the real world. So we're going to use a different term for that. We can still say our planar environment may be a 2D environment. And now instead of saying our state space is 2-dimensional, or now we're talking about a 3-dimensional state space in a 2D environment, we can say that as long as we're clear about what we mean. We're going to use instead the term degrees of freedom. So this is a 3-degree of freedom system, or a 3-DOF system, that lives in a 2D environment. Now, the dimensionality of the state space is specifically the size of that state space there. So the word dimension is overloaded. It'll be important to be clear about what you mean when you say the word dimension. Or you could use other terms like the size of the state space or the degrees of freedom of the state space. And so, without getting into too much details, I'll assert right now that given a 2D environment, we can either consider, given a 2D, and that is a planar environment, if we have single point objects like the tip, it will be a 2-DOF system. If we have rigid bodies, that is, single objects that take some extent in space, it will be a 3-dot system. Now, before we move up to a 3D space, which will highlight, we can build on some of these questions of dimensionality and dots, and we'll also highlight some of the points that I made earlier regarding the representation of particular states within that state space. I just want to take a quick aside to draw a parallel between, or to draw a comparison between this continuous state space and, of course, a discrete state space. Now, one thing we could consider is, let's consider, for instance, a planar state space that is discrete. Perhaps we can represent it by a chessboard. And now, I'm not very good at chess, so let's just go ahead and use my first chess board, which is 3x3. And we can say, rather than the entirety of the whiteboard, we'll have just these spaces. And our piece that we care about, the end result of my system, it's not going to be able, it doesn't make sense to consider everything here. Because if my marker is here or here, that doesn't change the nature of the game, which is something like this whiteboard, this chessboard. I suppose we could call it a tic-tac-toe board or something like that. In this case, because we have just a small number of states that our system could be in, we can go ahead and label them directly. Let's just give them letters. I. And now we can say that our state space is just a set of all possible states that our system can be. What's the size of this state space? Well, you just count them. There's 9. Now, the way I've drawn this right here is a 2x2, or is a 3x3 two-dimensional planar environment. But this is the reason for drawing it like this is both in terms of an ease of drawing and perhaps a correlation to the two-dimensional continuous state space. We'll talk more about this mapping between discrete state spaces and continuous spaces when we talk about discretization and function approximation later on in this course. But let's go back to this idea of this being a chessboard. And let's actually put a chess piece down, like with the indication that the tip of my marker doesn't represent a tip of a marker, it represents a chess piece that lives in this particular environment, and perhaps it's a knight, a horse. And it's unfortunate that the piece that I would like to use is one of the hardest to draw, but I'll give it a shot. And let's put the knight up here in part A. There we go. So now we have our piece up here in square A. And if you know how chess works, then the system dynamics, we're not talking about the tip of my marker, we're talking about this chess piece. The system dynamics, what I'm allowed to do in terms of updating the state of this piece, it can only move from here, either to position F or to position H. On this 3x3 chessboard, those are the only two transitions available to this piece. Considering the system that is a robot that behaves according to the laws of chess, there's no intrinsic connection between the position of the robot in 2D space and the layout of these states. I could just have easily drawn my state space as a 9x1 row of states. Again, A, B, all the way up to I. And again, if my, I'm just going to draw a circle this time, if my knight were in state A, then the destination is C, D, E, F, oops, F, G, H. The two destinations could be over here. So the layout of a discrete state space is irrelevant. All that matters is what the elements are in that state space, what the states are that are achievable, and what the transitions are, where things can go from one state to another. That being said, for the sake of illustration, it often makes sense to consider a 2D planar discrete environment that has a very specific set of transitions, where instead of having a knight, let's consider instead a king. Where each king can move in one space in any direction. I guess the king is allowed to move diagonally. We may want to restrict it to not even diagonally, just orthogonally. And that could just be for illustrative purposes. So we don't have to go ahead and define the set of transitions, the set of system dynamics that are allowed in a particular discrete state space like this. Just like when we're considering a planar environment in continuous state space, and you have your point on the board, and you move it around, we have some intrinsic, some inherent understanding that we can move in any direction of like L or H, or we can rotate in any direction A, alpha. If we do that, if we say that, let's just assume this discrete state space behaves similarly to a continuous state space in a planar environment, well, this will be known as a grid world environment. And so this grid world environment we'll be returning to this grid world environment a lot as illustrations, as examples for our robotic problems. But as always, it's important to note that this is just an environment. This is just an example. And it is a very simple example to be representative of the problems that we'll try to solve. But we shouldn't, and we should always be aware to not take shortcuts based on what we assume will be the way transitions happen, because that's how they happen in a grid world. Again, we don't want to assume that the knight can end up in position D from position A, because we've laid it out on a chessboard. However, the system dynamics may be different. There's another caveat to consider, and that'll be that may show up when we go ahead and bring a rigid body into this 2D environment. Rather than just considering a point, I'll go ahead and erase these so that we can reuse the same drawing. What if we had a similar sort of thing being the eraser? I'll go ahead and draw our robot system. And for the sake of completeness, I'll give it an orientation. One side of it is going to be the head, and the other can be the tail. Or maybe you can consider this a destroyer in Battleship. Which means now it has some orientation. Again, we're going to make sure that it only has discrete orientations. It can either be like this, which is it's pointing to the right, or it could be like this, where it's pointing down. We could have something where it's pointing the other direction, and that's pointing to the left. And now, in this case, with our rigid body in our 2D environment, in our 2D grid world, so we're going to say this is the 2D grid world where it has connectivity according to sort of the intuitive positions. Now we have some new states that this has. So this robot could be in the state A, pointing to the right. Or it could be in the state A, pointing down. And so on. Now, there's one thing to note in here, that the state A, but pointing to the left, doesn't exist. It's not in the state space. There's no way of putting this robot in such a way that it's pointing to the left and in state A. Keeping in mind that our system, our environment is defined by this, our mathematical world does not admit the possibility of A to the L, or of A and L. Now what this indicates, and what this is meant to illustrate, is that there is a difference between the states that a robot can take, the states that a robot can achieve, or can be in. That is, again, to go back to our earlier terminology, there's a difference between the mathematical quantity that's used to capture the time history of inputs, even if they're motional inputs. There's a difference between that and positions in the environment. And so, even though it's easier to talk about a state that the robot is in as the position in the environment occupied by the state, that is just a shortcut in terminology. Positions in the environment and mathematical representations of the time history of inputs, of motional inputs to a robot, are fundamentally different quantities. So I'll go ahead and be a little bit more clear here, in that this grid world environment, this A through I, is a representation of the environment. And elements within this environment, points within this environment, come from a discrete space. And we can talk about individual points within this environment as point A. And in practice, it may often be useful to talk about that. We will give that a term, and that's not going to be a state of the robot. Instead, we're going to say that the set of all positions in the environment we're going to call that the operational space. And in sort of an analog between the state space and states being points in there, we'll often use the shorthand notation to say that a position in the environment we will call an operational state. But it's important to note that this operational state is not a state of our system, because it doesn't describe the time history of inputs to our system. In this case, the operational state A, the position in the environment A, has no bearing on the time history of inputs to our grid world destroyer. Okay. To contrast with this, we will define our actual state, our robot state. Let's say we'll define the state of all, or the set of all robot states as our configuration state space, and our robot state, a single robot state, we'll call our configuration state. And this now, this configuration state, is an actual state of our system. These two, the operational space and the configuration space, they're correlated. Our robot lives in the environment. So a particular configuration state represents some collection or some subspace within our operational space. So there is a connection there. Sometimes it may seem that it's easy enough to decompose our robot state, our configuration state, into a component that is our operational space, that is an element of our operational space. That may not always be the case. And again, when we go to the 3D examples, we'll be able to see that in explicit detail. Nonetheless, there is, as always, a connection. And we're not going to go into it in this class, but there is an entire course worth of material on this about how to relate these two, and in fact going into more detail about what happens with rigid bodies in space. That field is known as kinematics. And the process of going from a configuration state, a true state of the robot, something that has captured the entire time history of motional inputs, to the operational space is known as forward kinematics. The process of going from perhaps points within the operational space, I'll put these in quotes just to be clear that's not a state by the definitions of this class, to go from perhaps points in operational space to configuration states that can interact with or represent some of those. That's known as inverse kinematics. And forward and inverse kinematics are, again, problems that show up in robotics tasks and show up in robotics problems. We're not going to go into that in this class. Just know that it's there. But now, to highlight, again, the further distinction between perhaps a configuration space and an operational space, the fact that the set that defines all points within the environment versus the set that defines a representation of the entire time history of motional inputs, let's move up to an example in an environment that is 3D. Now, for the sake of this example, we'll stick with a continuous state space. And in contrast to planar, I'll call it a space filling, I don't know, let's call it a spatial environment. And again, I'll just consider the tip of the marker. But now in free space. And so we can go ahead and put this marker everywhere. It's not going to draw anything in the air, but we can go ahead and do this. How might we describe the position of the marker tip? How might we describe the time history of motional inputs when I don't care about what happened in the past, only where I'm going to go in the future? How would I would describe this as a state? Hopefully this is all reviewed to most of you, so we'll just plow right ahead. If not, feel free to pause the video and think about this on your own. We can go ahead and describe this state of just this marker tip. We can talk about it in terms of 3 values. We'll still talk about the length away from this vertical edge. We can talk about the height above this horizontal edge. And we'll talk about the depth away from the board. And that'll cover all this space. We could similarly talk about something where we're talking about strictly the distance away from this particular point that we described. We can talk about one angle, which may be the elevation angle, or the azimuth angle. Sorry, One angle, which is the elevation of the point with respect to the horizontal plane. That'll still be our theta. And then we can talk about the angle where we have to look back across the vertical axis in order to get back to that point. We can call this B. Again, both of these are in R3 now. So again, it's a 3-degree of freedom, a 3-dot space, a 3-dimensional space. That's why these are often called 3D spaces. When we're talking about single points, the dimensionality matches or lines up. And again, we can see we have multiple representations of the state. In this case, they're both 3-dimensional. What happens now when we consider a rigid body in our spatial environment? We still care about the position of our marker, but we now also care about the orientation. If we're trying to write on the board, we can only do so when the tip is pointed into the board. If I flip it around, it's not going to work. So in this case now, our state, x, needs to incorporate information about the time history of translational inputs, like we did up here with just the tip, but it also needs to incorporate the time history of rotational inputs. Now we can go ahead and take that information and collect that into our state and say the time history of translational inputs will be part of a translational component to our state. And then the time history of angular inputs, of rotational inputs, will be an orientation component to our state. Now, I won't get into the details here, but there is some mathematical trickery that we can use to prove that we can decompose translational motions and rotational motions into a translational state and an orientation state separately. But we'll go ahead and assert that and say that for our translational state, we can go ahead and reuse the same definition up here. And therefore we'll only consider our orientation state as an add-on to get to our rigid body state. So for our orientation state, we need to consider a way of encoding the time history of rotations alone on this rigid body. Well, we can use that specifically, the time history of inputs, the time history of rotational actions, to come up with a particular representation of state. And we can say perhaps that we will achieve some particular orientation by first rotating about one axis, maybe rotating about a second axis, rotating about a third axis, and we can come up with the representation of our orientation state, which we'll call our Euler angles. We need to do these rotations around about 3 axes to be able to get any arbitrary orientation of our rigid body. And for out of convention, we can call them our roll, our pitch, and our yaw angles. Again, we'll need some mathematical proof that says that these 3 angles can capture our full orientation state. And again, you can go to a lecture on kinematics to get that proof. But we'll go ahead and say that there is one representation of orientation known as these Euler angles. In fact, there's many Euler angles, but 3 angles are enough. 3 angles are enough, the right 3 angles are enough to describe the entire history of angular motion into a single state representation of orientation. And therefore, we can see that this has 3 real numbers associated with it. It's a 3-dimensional state. Now it's important to note that I'm using R3 and saying a 3-dimensional state just as an indication that there are 3 real numbers associated with this representation of state. It's not the same as a 3-dimensional Euclidean state. There are points within this space where the topology of the space, where the behavior of that space is different than an x, y, z translational state. And in practice, that poses challenges for using this particular representation of state within the math that we will define systems that have an orientational component to them. If any of you recall the movie Apollo 13, there's a scene in there where they radio Houston and say, all I want for Christmas is a 4th gimbal. In the case of the Apollo 13 lunar module, they were capturing and maintaining this orientation state using a gimbal for each one of the Euler angles. So they had 3 of them, 1 for each. And that caused problems when the system behaved differently than intended. And so because of this, there have been additional representations of state that we use for orientation. I'll go ahead and describe one more, which we'll call a quaternion. We'll call it Q. And we can identify this by 4 numbers, which we'll label A, I, J, and K. Now, I'll say that this is in R4, in that there are 4 numbers that are used to represent this particular state. However, it's representing the same state, the time history of angles and of angular motion, of angular inputs to our system. I'll give one more representation of state, and this we're going to call our rotation matrix R. Also known as the direction cosine matrix, DCM. And our rotation matrix is now a 3x3 matrix. Well, if it's a 3x3 matrix, that means it has 9 real numbers associated with this particular representation of state. Well, these 3 quantities are all representing the same logical object. They're all representing a particular state, a particular time history of angular inputs. Well, how do we reconcile the different sizes of these spaces? Well, it turns out there's additional constraints on these particular representations. In this case, we're not allowing all elements of R4 to be allowed to be called quaternions. We're only allowing those that are normal, that have magnitude of 1. Well, this provides a constraint, which means that we're actually accomplishing a 3-dimensional subspace of R4. And so once again, we have our 3-dimensionality of our orientation state. What about our rotation matrix? We know that this is another representation of the same kind of state. It has 9 numbers associated with it, but it's representing a 3-degree of freedom space. What does that mean? We need to have 6 constraints to get the number of degrees of freedom back down to 3. Those 6 constraints come from the fact that this matrix, the only 3x3 matrices that we will allow to be rotation matrices, are orthonormal matrices. And we're going to call this SO3, the special orthonormal group of dimension 3. In fact, all of these are representations of SO3. What this means is that every column in this matrix is normal, has magnitude 1. So that's 3 right there, 1, 2, 3. And then every pair of columns is orthogonal. And there's 3 pairs, so that those are the remaining 3. So now we have 6 constraints here from these 9 real numbers. We have 1 constraint here on these 4 real numbers. We don't have any constraints here on these 3 real numbers. Together, this indicates that our orientation state is 3 degrees of freedom. And coupling that with the 3 degrees of freedom of our translational state, we have our 6-DOF system. A rigid body in a spatial environment is a 6 degree of freedom system. A state space of dimensionality 6. Now, these examples were specifically considering a system that was this rigid body, or just the tip of this rigid body. This particular marker is the system that gives us these values. What if instead we're considering a robot that manipulates this particular marker system? What if instead we're going to consider as our actual system my arm that's holding onto that rigid body, again, in our spatial environment, in free space. Well, now what are we talking about? Yes, we still have this rigid body, and it's in free space, but we're no longer considering that the rigid body is a system that we're going to mathematically formulate. We're instead going to consider my arm. This arm, holding firmly onto this rigid body, is able to manipulate this rigid body through space using a different set of inputs. Before we were talking as if the marker itself had the inputs to move through space or rotate through space. In this case, what are the actual inputs that we have? What are the inputs to our system, that is the arm, that can be used to manipulate that rigid body? And then we'll need to take those inputs and collect that into our state representation that captures the time history of those inputs. So why don't you take a moment right now to play around with this. Grab a rigid body and move it around, manipulate it with your arm. Capture how many inputs you can apply to that system, and use that to just come up with a definition or a representation of the state of your arm, of this arm. So pause this video, write down what you can, and then come back and join us and see if we have the same definition of state. Okay, so let's just get some examples up in here. What are some of the inputs that we can take to manipulate this rigid body? What are the inputs that we can feed to our system, the arm, to manipulate this? Well, as we're moving around, one of the things we can do is we can look at our elbow. We can go ahead and extend our elbow. That's an action that we can take. That's an input to our system. Okay? What are other things we can do? Well, it's being held by our hand. We can go ahead and twist our wrist. That's another motion. And so on. We have a bunch of actions that we can take from just our arm that can go ahead and manipulate this rigid body. So let's take our actions, take our inputs, and collect them all into our configuration state. And what we'll go ahead and say is that each input is independent for now. we'll say that each input that we can apply is independent. So each one will contribute to one dimension of our configuration state. That's going to need a little bit of mathematical finery to ensure, to prove. But for now, we'll just go ahead and assert this. Similar to the breakdown before of rigid body motion and translation and rotation. The inputs to our arm can similarly be broken down for each one of these independent degrees of freedom. And what are these degrees of freedom? Let's start at the top, at our shoulder. What can we do? We can raise or lower our shoulder. Call that S1. We can move our shoulder forward and back. S2. We can twist our shoulder. S3. Our shoulder is a ball and socket joint that has 3 degrees of freedom. What about our elbow? Well, our elbow can only do one thing. It's a hinge joint. It can only move in one direction. Call that 1. Our wrist? Well, our wrist is similar to our shoulder. It's a ball and socket effective joint. And so it can move in, again, in 1, 2, and 3 dimensions. And if we're just considering our arm down to our hand, that's all we have. We have these 7 motions, which means our configuration space is also part of this is also 7-dimensional. We have 7 quantities that we need to use to define our configuration state. So we have the 7 degree of freedom state space of our arm being used to manipulate the 6 degree of freedom state space of the rigid body system. We have 2 different systems in our environment, and of course, the states of those systems are related. The inputs to our arm generate outputs that are the inputs to the rigid body system. And they have very different state spaces. This is the rigid body space of dimensionality 6. This is the configuration space of the arm of dimensionality 7. And going back to some of the earlier terminology, when we have our configuration space, when we have our configuration state of our robot arm, it is living within the environment that has that operational space of degree 6. The operational space of the arm is, in fact, directly correlated to the configuration space of that rigid body at the end of the arm. But just as we can see that the configuration space of the arm is 7-dimensional, and the configuration space and the operational space of the arm is 6-dimensional, in fact, the operational space of the arm has 3 linear translational degrees of freedom, while there are no translational degrees of freedom in the configuration space at all. This tells us that the configuration space and the operational space are completely different entities. They're different mathematical quantities. And so in this rigid body system, for this rigid body system, even though the configuration space and the operational space are both 6 degrees of freedom, in fact are both spaces that have 3 translational and 3 rotational degrees of freedom, the configuration space of that system, which is the state of that rigid body, the marker space system, and the operational space are still distinct quantities. They're different mathematical entities, as we can see here. We can use the relationship of the configuration space of this arm to the operational space of this arm, and similarly the configuration space of this system to the operational space of this system, and the connection between these 2 spaces, all the various problems that show up in the field of kinematics, to relate all the systems within our environment. Now, you'll note that the dimensionality of the configuration space is 7. There are 7 degrees of freedom that our arm can take. Nonetheless, the dimensionality of the operational space, the number of positions that the end of my arm can be in, is of dimensionality 6. Now what does that mean? Can you come up with some clear consequences of the difference in size of the configuration space versus the operational space? Well, what this means is there are far more configuration states than there are points in operational space. And so for every point in operational space, there are in fact an infinite number of configuration states that can be assigned to that particular operational point. So for instance, let's say I wanted to get the tip of this marker to my nose. I can do so, and I can do so in a number of different ways. There are a number of configurations, a number of states that describe the history of emotional inputs to my arm that all result in the marker being held to the tip of my nose. And to be clear, they are states in that they are Markovian states in that that representation of the time history of inputs is directly relevant to the output of note. In contrast to before when we were talking about, let's say, drawing an image, if we only care about the point and where it needs to go, even still, all 7 of these states are necessary. All 7 of these dimensions are necessary. Again, as an example, let's say we have the tip of the marker at the nose. I could have the tip of the marker at the nose with my arm in this particular configuration state, or it could be in this configuration state. Now let's say, it doesn't matter how I got here, it doesn't matter the past, all that matters is I want to now move the tip of the marker to my ear. Well, when I'm in this configuration state, I can do so. I can go ahead and just, in a straight line, go to my ear. But if I'm in this configuration state, and I try to move the point in a straight line to my ear, well, I run into the wall. The configuration of my arm interacts with the environment in such a way that this is no longer possible. I get part of the way there, but then I have an issue. And so in order for me to get there, I would need to move to a different configuration and then move there. And so this is a state that, this is a Markovian state that is a different size than the operational space. Now, just as an aside, arms are real things, and things we're holding in our hands are real things. Can you conceive of a way in which our brains, our controllers, the computation that goes on up here, decides which of the infinitely many configuration states we will inherently go towards when we pick a particular operational space that we want to go, that we want our hand to be at? Think about it, see if you can come up with something. I'll explain it in the next lecture. Now, another set of terminology that may help in relating configuration spaces to operational spaces. As we saw here, this configuration state is R7, our operational space is R6. If, for instance, we were not considering our shoulder, our arms are strapped to our side, and we're only considering our elbow and our wrist. Well, now we lose these 3 elements of the state, of the configuration state. This new smaller robot, that's just the elbow down, has a configuration state, let's use a different color, R4. Now this is much smaller than the dimensionality of the operational space. What does that mean? That means that some elements of the operational space are no longer achievable. There's no way that with this particular system that I can take the marker and touch my nose. Okay, so if we have a dimensionality of the configuration space that is lower than the dimensionality of the operational space, we have what's known as an underactuated system. Now, under-actuated systems are in fact still quite valuable. There's an entire subfield of robotics and courses that you can find devoted to under-actuated systems. It may be out of necessity, in that our robot just is not as capable. It may be out of a design decision, whereas when we have fewer actions, when we have fewer inputs that we can send, we perhaps don't need to spend as much energy. And in fact, we can make use of the techniques that we have to develop in systems that are not as capable, and we can apply them to systems that are not necessarily under-actuated, but that have enough degrees of freedom. But we can apply those same techniques to accomplish additional goals, additional objectives on the particular tasks. The under-actuated system is in contrast to a fully actuated system, where, in part, if your configuration space can completely span your operational space, we'll talk about a fully actuated system. And now, just to be clear, it's not, if the configuration space is less than, if the size of the configuration space is less than the size of the operational space, it must be under-actuated. It's not an if and only if. You can have a multi-dimensional configuration space that does not accomplish the goals of a fully actuated system. For instance, if we just had a bunch of elbows, so let's draw it in the plane where we have our shoulder, and these are all just elbows. How many there are? 1, 2, 3, 4, 5, 6, 7, 8. Oh, 8. This is an 8-degree of freedom configuration space. Each one can take on some angle. However, no matter how we drive these angles, there is no way that this tip will ever come out of the board over to here. So this would still be an under-actuated system. The question is whether the space defined by the configuration states can span the space defined by the operational space. A fully actuated system is able to span that completely. One of the requirements for a fully actuated system is that at least the dimensionality of the configuration space has to be equal to the operational space. Now, if not only is if we have a fully actuated system where there is that one additional criteria, which is, as we noted before, here we have 7 angular states, whereas our 6-stop system has 3 linear states and 3 angular states. If every one of the degrees of freedom in our operational space is directly achievable by a set of by a state within, or a dimension within our configuration state, then we have what's known as a holonomic system. So a holonomic system is a fully actuated system where there is a one-to-one correspondence between the configuration space and the operational space. Okay. So, to pull this all together, we talked a lot about the various terminology. Hopefully this cements in your mind the concept of a state. This does bring up one final problem that we didn't talk about in our enumeration or in our listing of robotics problems. And that's this question. Again, let's look at this problem statement. Let's say we're given our system, our inputs, or let's say we're given our inputs and our task, whatever our objective is. So our task, which we can represent by our z, and our inputs, which we represent by u. let's find a particular mathematical form of the state. Do we want to use Euclidean coordinates for the linear state, or do we want to use polar coordinates for the linear representation of the state? Do we want to use Euler angles, or quaternions, or DCM, for the transformation matrix? Do we want to come up with a completely different form, a different mathematical entity that represents the state? This problem is the problem of state representation. And as far as I can tell, trying to come up with a process that can accomplish this has not really been addressed very thoroughly. Right now, it all requires an engineer to go ahead and look at a task and come up with a particular state representation. And doing this for different tasks is still in itself a challenge, and may be an interesting problem to tackle, finding a particular robotic task and finding the right state representation, the right mathematical form that accomplishes these tasks in some manner of effective way. We can talk about how this may relate to the questions of underactuated versus fully actuated versus holonomic. If it's a fully actuated system, is there a state representation which is holonomic? If we have a particular system, is there a state representation which is minimal? Euler angles require only 3 numbers for a 3-dot state, versus quaternions which require 4, or the DCM which requires 9. 3 is minimal. On the other hand, are there mathematical characteristics of the minimal state which do not hold nicely, and therefore we need to apply a non-minimal or redundant representation of state? There may be other criteria in here. If we may talk about questions of computational efficiency, that the functions f and z and h that apply to that state, maybe they can take on different forms. Maybe there's a representation that lets f and h be linear versus another representation which makes them nonlinear. Linear systems are considerably easier to deal with. Perhaps that's a problem that can be addressed with the state representation problem. And there's many, many, many more considerations where if we allow the state representation, the choice of the form of the state to vary, we may go ahead and find ourselves solving a problem easier or better. And so we won't discuss that in this class in terms of a process, but as of right now, we can consider problems where we go ahead and directly apply our ingenuity and our creativity to the problem statement to find new state representations. And who knows, perhaps you can be the one to formalize this system in between here and go ahead and come up with a new process and a new set of tools and techniques that can automatically or that can computationally determine the right state representation for a particular robotics problem. That's all I have to say about states and systems. Starting next week, we'll go ahead and actually work on the problems of planning and control with regards to discrete systems. So stay tuned and have a good week.